Okay, we will go through the exemplar problems in the class 12 physics chapter 7 alternating current. Okay, so I'll show you some information, basic information. When you have a DC voltage or current, this is DC means the direct current, so it won't change over the time. So this is time versus, let us say, voltage, that is constant. Okay, this is direct current, this is DC. But if you take a alternating current, the waveform varies like this, that is during the time it goes positive, negative. So we need a common value to represent both DC. So to represent DC and both in the same unit, we use RMS value. RMS means, let us say, in this waveform you take a couple of points, 1, 2, like this. So at this instant, what is the amplitude? So you have to take the square and divide it by the average number of points. So root mean square, okay, value, RMS value, root mean square. This is how root mean square is computed. Each instant square of that amplitude divided by the total number of points. Okay, so RMS value for the so now this value will be equal to this DC value. Okay, for the sine wave we can say V RMS equal to 0.707 into V peak. Okay, V peak only for the sine wave, this formula. So here various power formulas. Power equal to voltage into current. If you substitute for voltage V equal to IR as per the Ohm's law, if you substitute IR here, then power will become I square R. So power equal to VI, same thing can be expressed power equal to I square R. If you substitute I equal to V by R, from this I equal to V by R in this, then you get V square by R. This is also power formula. So depending on the what is given, we can use different formulas. V square by R, I square R, VI. Okay. So here VRMS equal to 0.707 into V peak for the sine wave. So V peak equal to the 0.707 is nothing but 1 by root 2. So okay, V peak equal to root 2 into VRMS. Okay, the root 2 will be like a 1.4, I think. So it can be voltage or the current. So if you take a circuit, let us say few resistor connected to a voltage source, V equal to VI, both voltage and current, they are in phase. Okay, but if you take a capacitor, here current leads voltage by 90 degrees. This is current is leading. So capacitive reactance X equal to 1 by omega C. Omega equal to 2 pi F. 2 pi F is the frequency of this voltage source. Okay, it can be F or V. Okay, so we have to remember this term is the frequency. So it can be written as V or F. So now for a DC voltage, see here, if you take this frequency for DC, it will be 0. 1 by 0 is infinite. So for a DC, Xc will be infinite, okay, for the DC. Because for DC, frequency will be 0. 1 by here 0, if you the denominator will become 0. 1 by 0 is infinite. So, but for other frequencies, if you increase the frequency, so this term will increase. Okay, 1 by more number means then it will be less, Xc will be less. So I is more when frequency is high. Okay, when you increase the frequency, what will happen? This term will be more. So 1 by anything more, then it will be Xc will be less. When Xc is less, the current will be more. Okay, I increases when frequency is high. Okay, frequency is high means Xc is low. For inductor, you see connected here capacitor current leads voltage by 90 degree. In inductor voltage leads current by 90 degree. Okay, voltage leads current by 90 degree. Here 2 pi, here 1 by 2 pi we see here, just it is not in the denominator. 2 pi will see 2 pi VL. Here for DC, because this is not in denominator, when frequency is 0, XL will be 0. Okay, so for DC V equal to 0 here. So in this case, I decreases when frequency increases. Okay, so here I increases when frequency increases, here I decreases when frequency increases, because of this formula. Okay, here 2 pi FL, there 1 by 2 pi FC. Okay, in the RLC circuit, where you circuit have resistance, inductance and capacitance, then you compute impedance like this Z. So the voltage by impedance is the current. So at resonance, this XC will be equal to XL. This term will be 0. That means Z equal to R at resonance. Okay. So the current will be maximum at resonance. This is the resonance frequency, that is angular frequency, that is equal linear frequency 1 by 2 pi rho f of LC. Okay, delta W, this is the bandwidth, R by 2L. Quality factor at resonance, this formula, omega naught L by R. Resonance frequency bandwidth, this is the tan phi, angle between voltage and current, SC equal to XC minus XL by R. Power in the RLC circuit is VA cos phi or I square Z cos phi, anything you can use. Based on the pi is the angle between voltage and current, cos phi equal to R by Z. Okay, these are the various formulas for the angle. So this is for the transformer case. Input power equal to output power for the 100% efficient transformer. Power equal to VA, voltage in the primary, current in the primary equal to voltage in the secondary, current in the secondary. So input power equal to output power, 100% efficiency. But if you say 95% efficiency, then the output power equal to the 0.95 into the input power. Okay, 95% efficient, only like that you have to. So the output voltage depend on the number of turns in the secondary. Okay, NS. Output voltage is directly proportional to the NX. Okay, primary by secondary equal to V secondary. Okay, so if the RMS current at the at 50 Hz frequency AC circuit is RMS current is given, the value of the current is 1/300 second. Okay, time is given, so you have to use that formula to compute the value of the current. Okay, given is the 50 Hz frequency, RMS is given. So this is the magnitude of the current at any instant. Okay, so now this is magnitude is equal to root 2 into RMS. Okay, I max equal to root 2 into IRMS. IRMS 5 amps they given. So root 2 into 5 is the I sine of omega t, omega 2 pi f, 2 into pi 3.14 into ft, t is given 1 by 300 into f50. So after simplification, sine 5 by 3 is root 3 by 2. So you will get this answer. An alternating current generator has a internal resistance. Okay, this is the internal resistance and internal reactance. It is used to supply to a passive load containing a resistance of the reactance. for a maximum power, this for the maximum power to be delivered from the generator to the load, then the load resistance, load reactance, for the maximum power the transfer of the load reaction should be same. Okay, that is this internal reactance plus the load reactance should be 0 when you add. That means the both should be equal, xc equal to x minus xl. Okay, this is when a voltage measuring device is connected to the AC mains, the meter shows steady input voltage 220 volt. This is in our house. This means, so that is reading the actually the DC, that is RMS value of the AC voltage. That is nothing but like equivalent to a DC voltage. That is why it is steady. It's not varying with the time. So the meter reads not voltage, but this is nothing but the RMS calibrated to, okay, RMS value is equivalent to the DC. To reduce the resonant frequency of an LCR circuit, the generator, another capacitor, that we have to increase the capacitor at the resonance frequency. Okay, this is the frequency at resonance, angular frequency at resonance. You see 2 pi square root LC. If you want to reduce the resonance frequency, we have to increase this inductance or capacitance. The WCT so if you increase the capacitor, this will reduce. Okay, so how do you increase the capacitor? When you connect two capacitor on parallel, so the total capacitance is addition of these two capacitors. Okay, parallel. When you, so that's why it will be, capacitance will be more. When capacitance will be more, the F will get reduced. So they are asking, we have to reduce the resonant frequency. That means capacitance should be increased. That is in the denominator. Okay. So here, if you iron core in the inductor should, if you remove this, then inductance will decrease. That won't help. Similarly, if you remove the dielectric from the capacitor, capacitance will decrease. That won't help. Okay, this generator frequency should be reduced. Generator frequency is nothing to do with the resonance. Okay, resonance is depends on the L, the square root LC, as I already showed you. Which of the following combinations should be selected for better tuning of the LCR circuit for a communication? Okay, see, better tuning means it's a quality factor. Okay, quality factor. How to improve the quality factor? When R is less, L is high. For the quality factor formula, you have to see 19. Okay, this is the quality factor. So this will be large when R is low and R L is large. Okay, quality factor when R is low or L is large, then only we can improve the quality factor. R is low or L is large. Okay, R is low or L is large, then that will increase this quality factor. Okay, based on that, R is low, L is large, so you can choose this combination. And inductor resistance is inductor reactance is given. Resistance or LR circuit is connected in series with the 6 voltage source. The power dissipated in this circuit first. So power, we have to find out the current. Then from that we can find the power. So the given this reactance and resistance are given, voltage source is given. So impedance we are computing this formula. Then we are finding the IRMS. So this is voltage by the impedance. Okay, this is the current. Then we are finding the power using this VI cos phi, voltage into current into cos pi. Cos pi is R by Z. So cos pi has various formula. In that we are using R, resistance by impedance. Okay. So if you use this, then you will get 14.4. This is the cos of the angle between voltage and current is R by Z. Okay. The output of a step down transformer. The step down transformer means output voltage is less than the input voltage. Okay. This is measured to be 24 volt, then connected to a 12 volt. This is the power of the bulb. The value of the peak current. Okay, this is step down transformer power. So the input power is equal to the output power. Power equal to VI. So VI, this is the power, is equal to the 24 volt into the I output. From that we can find out the I RMS equal to 12 by 24, that is 0.5 ampere. Okay, then peak current will be root 2 into the RMS current. So we have found the peak current here. So this is the current, the value of the peak current. As the frequency of an AC circuit increases, current first increases. Current increases and frequency increases, current increases. I already showed you which combination and frequency increases, current increases. Okay, then decreases. The combination of circuit element is most likely at resonance. Frequency Z is minimum. Okay, Z equal to R, so the current is maximum. So it will be the resistor, inductor and capacitor circuit. Okay. As the frequency of the circuit increases, the current first increases and then decreases. 16. See, current first increases. This is current versus frequency. Current increases and then decreases. Okay. So this is for the RLC circuit. So this is the frequency, this is the current amplitude. Okay, current as the frequency increases, current first increases and then decreases. So that's RLC circuit, resistor, inductor and capacitor circuit. And alternating current consists of the elements in series. Current increases with the increase in frequency. of the supply. Current increases when you increase the frequency, means it is the capacitive circuit. As I already explained you initially, when you increase the frequency, the capacitance will decrease, so the current will increase. Okay, xc will decrease, but the current will increase. Current increases, increasing frequency of the supply. Which of the following elements or like constitute? Okay, the resistor and capacitor. Capacitor should be there. Resistor won't affect. Only a capacitor. Okay, resistor and capacitor, only a capacitor. 7/9. See here, when you xc, so increase the frequency, then xc will decrease, that means current will increase. Okay, r is independent of the frequency. Okay, the current through the r independent of the frequency. So but for xl, it increases with increase in the reactance increase in frequency. xc will decrease with increase in frequency. When xc decreases, that means current will increase. Okay, so that is why this capacitor should be there, and that when you want to increase the current for increasing frequency, capacitor should be there. Electrical energy is transmitted over large distance at high voltages. Okay, which of the following statement is correct? See, the resistance is inversely proportional to the area of the cross section. For the thin wire, resistance is increases when A decreases. Okay, resistance will increase and A decreases. Correct. Even there is a okay for high voltages to minimize the power loss. That is correct. Current is okay. See, it is used to reduce measuring the end using this. This is okay. See, this is what this is wrong. Why it is wrong? When you make the area of cross section less, then resistance will increase. That will increase the power loss. Okay, that is why this is wrong. Transmission lines can be thinner. Okay, thinner, no, you cannot make it thinner because the resistance will increase. Rho L by A is the resistance, that will increase the voltage drop, power loss more. So this is wrong. All the other things are correct. Power is transferred from the driving source to the driven. Okay, this is the power formula. VA cos pi or I square Z cos pi. Okay, the power factor cos pi. Okay, this is correct. The driving source can give no energy to the oscillation. Okay, okay. This angle always when it is cos phi is more than 90, then only it will be negative, because this angle cos angle is always less than 90, then it can't be negative. When an AC voltage, so voltage of 220 applied to a capacitive circuit, okay, the capacitor, this maximum voltage between the place is, no, this is wrong. This is the RMS value. 220 volt is the actually RMS, that is not the maximum value. Okay, so the peak will be square root into RMS, that will be 311. The current, this is important. Okay, the maximum voltage across the, this is AC voltage, that is RMS. They are asking the maximum, they are saying maximum voltage 220, it will be more than that. The current is in phase with the applied current, leads voltage by 90 in the capacitance. So this is also wrong. This is wrong. This is also wrong. The change in the place is in phase with the applied voltage. Okay, the voltage is in phase. Okay, current leads the voltage. Voltage is in phase. Power is delivered to the capacitor is 0. Okay, yeah, because the voltage and current are in 90-degree phase. So the power VI cos pi cos 90 is 0. So the power delivered to the capacitor is 0. This is correct. Okay. See, this is the voltage and current. See, the current leads the voltage by 90 degree. Okay. Here the peak is there for the voltage. Current is so the current leads the voltage by 90 degree here. Current leads the voltage by 90 degrees. Okay. The line that draws power supply to your house from the street has zero average current. Yes, it is a sinusoidal wave current. So this is a zero average current. The average voltage 220 volt average voltage RMS. This is not the average voltage. Average voltage will be zero. It's only the RMS voltage, not the average voltage. Voltage current are out of base. No, this is not the correct. Voltage and current possibly differ ways such that so it will be less than 90. Okay, this may be true. Okay. If an LC circuit is considered analogous to a harmonically oscillating spring block system, so which energy of the LC circuit would be analogous to the potential energy and which is the kinetic energy? Okay, this is the capacitor will be analogous electrical energies to capacitor source electric energy that is analogous to the potential energy, and the inductor store the magnetic energy that will be analogous to the kinetic energy. Magnetic energy analog to the kinetic energy and the electrical energy is analog to the potential energy. So this is the free flux system. Okay, so they have explained at various how this LC circuit will also oscillation works. Okay, inductor is like a magnetic field energy, capacitor is like a potential energy, and inductor is like a kinetic energy. Draw an effective equivalent circuit of the shown here. This is equivalent. Very high frequency they are asking. Very high frequency. At very high frequency, this inductor will be a open. Inductor will be open. Capacitor will be short. So we have to use that formula XL formula. How inductor and capacitor will behave at high frequencies. See, this is the reactance formula for the inductance. Here 2πfl. If you increase the frequency, this will be increasing at high frequency. When XL is high means that it will be an open circuit. Okay, this will be open, this will be open. Similarly, if you increase the frequency, this will be more, but 1 by this, then this will be less. So this will be a short. So after simplifying, you say open. This inductor is open and the capacitor is short. So this is the simplified circuit. So here open, two open is there. So the current will come from this and goes to this is the simplified circuit. So the Z will be R1 plus R3. Okay, this is the impedance. Okay, so 15. Okay, the MC is given here. Study the circuit A and B and the answer the following. Okay, this is the circuit resistance and the RLC circuit. Under which condition would the RMS current in the source circuit should be same? When XC, this will be equal to this, X equal to XL, then it is like a resonant Z equal to R, only R. So here also R is there. So at when X equal to resonance, this current, the current in the two circuits will be same. Okay. Can the RMS current in the circuit be larger than that of the A? No, it can't be. So Z either is equal to R or greater than the R. Z cannot be less than R. So it can't be more. Current here can't be more than this. Because Z should be greater than or equal to R. Can the instantaneous power output of an AC source can be negative? Yes, instantaneous can be negative, but the average cannot be negative. Okay, instantaneous can be negative. So that is on AC source can be negative. Instantaneous power. See here, the instantaneous power can be negative. Here, see, this is instantaneous power. This is the power, this waveform. It can be negative, but average cannot be negative. 7.17. Instantaneous can be negative, but average cannot be negative. Okay, in AC LCS circuit, this current versus frequency is given. Find the bandwidth. Okay, show answer. The bandwidth 0.707 of the from the left to the right. So this is the peak current and 0.70 on the left and the other 0.7 on the right. And this difference is the bandwidth frequency. Okay. 17. So this is, suppose we choose the power W, for which the current amplitude is 1 by root 2, that is 0.707 times the maximum. At this point the power dissipated is off. Okay, between these two off power point is the bandwidth. So this is how the two frequencies, one on the left side, one on the right side and one on the left side, then difference is the bandwidth. So here this is the peak, means 0.707 of this will be somewhere here. So between these 2 points on the left side and the right side of the peak is the bandwidth. See the alternating current described by the graph. Okay, see I have said the only for the sine wave, that peak RMS current equal to 707.70 into peak current. But the square wave you have to compute using that RMS formula, that is square of the various samples divided by the number of samples. Okay, different from the sine wave, that is very important. 7.19. See here they are taking we have to take the average of the sample. One sample flat positive one, then other is negative 2. Two sample if you take, this is 5 by 2, that is square root of 2.5, it is 1.6. Okay, this is, you have to do the RMS computation. You should not use that 0.707 into the peak, that is C for the sine wave only. How does the sine of the phase angle by which power supply voltage leads the current? Voltage leads the current. Okay, voltage leads the current. Voltage leads the current. Voltage leads the current. This inductor, LCR circuit. Change as the frequency is gradually increased. Okay, primary. So 20. So it will vary from negative to 0 to positive. So you can use that z equal to square root of r square plus xc minus xl square. Then from that you can for this circuit. So how current varies when you increase the frequency. This thing changes when you increase the frequency. XL XC changes then from negative to 0 to positive. A device is X is connected to an AC source. The variation of the voltage, current and power. Okay, the voltage, current and power is given. Which curve shows the power consumption? This is the top. Okay, VI or I square R. Okay. What is the our power average power consumption? Okay, that is 0. Average. This is the power curve. Average will be 0. Identify the device X. So here important thing the which is current or which is voltage is not given. Suppose if they given this is the voltage and this is the current, that means current leads the voltage. That means it may be capacitor circuit. If this is current and this is voltage, means voltage leads the current, maybe inductor circuit, but they are not given here which is voltage or current. So it can be either L or C or LC. Okay, that is important. They are not given which is current and which is voltage here. So it can be an inductor or capacitor or both combination. So this is 0. This is the power curve. That is the top curve. This is the power curve. Average is 0. The circuit can be LRC or LC. Both alternating current and direct current are measured in amperes. So how the ampere is defined in the alternating current? Alternating is joules. Okay, joule 22. And AC current changes direction with the source frequency, and the attractive force would average to 0. Thus the AC ampere could be defined in terms of the same frequency, that is independent of the distribution of the current. Joule heating effect is such a property, and hence it is used to define the RMS value of the AC. See here, this Joule heating is used to define the RMS value. A coil of this inductance is given, resistance is given, is voltage is given, inductance, resistant voltage and frequency is given. Find the impedance of the circuit in the time lag between the alternating voltage and the current. So because LR circuit, so they given how to compute the reactance 2 pi FL, then the total impedance, then the phase between the voltage and current using this. A 660 watt load is connected to the secondary of the transformer. Primary draws the voltage. If the current flows in the load, that is the secondary current. What is the current in the primary? Comment on the type of the transformer is used. Okay, type of the transformer. So you have to find the secondary voltage to see the show answer. This is the power, output power, and the current is given from that voltage. So the transformer is stepped down because the input will be 220 volts source. So this is a step down transformer. Output voltage is less than the input. Step down, and hence half of the input voltage. Hence this current. Input power equal to output power. Okay, this is how this relationship works. So when output voltage more means output current will be less than the input current. Power will be same for the 100% efficiency. Okay. So when something is not given, then you have to assume the 100% efficiency. So based on this, you can get. Explain the why the reactance provided to the capacitor is an alternating current increase. Okay, this is based on that formula. These two based on that formula, XL formula 25 and 26. The capacitor does not allow the flow of the current through it, as the resistance across the gap is infinite, because for the DC it will be infinite resistance for the capacitor, because DC is 0, 1 by 0 is infinite, and an alternating current is applied across the capacitor. The plates are alternately charged and discharged. Current through the capacitor result of this charging voltage, that the capacitor will pass more current through it if the voltage is changing at the faster rate, that is frequency is high. If the frequency of the supply is higher, this implies the reactance offered by, because this is based on this simply formula, omega equal to 2 phi f. If you increase the f, then Xc will decrease. High frequency is more current. For DC it is like a open. Same thing is applied for the inductant also, but here it is 1 by Wc, but here it is not 1 by, it is just a WL. Okay, an electrical device, 2 kilowatt power line AC mains voltage. Okay, find these three. Okay, 27. We have to use this power formula. I showed you for power there are various formulas is there. Based on what is given you can use. So impedance and voltage square. So based on that you compute the impedance. Okay, based on the power and the voltage source. Then find the angle. Use this. See, 1 megawatt power is to be delivered to the power station. This is 10 kilometer away. They are using the pair of copper wires. Okay, 10 kilometer away, but pair of wires they are using. That means the total length of the wire will be 20 kilometer, because they are using the pair of wires. Calculate these things they are given. Okay, pair of wires. See, distance is 10 kilometer, but we are using the pair of wires 20 kilometer distance. So the resistance is equal to rho into L by A. They are given the density copper wire. This they are given. L is the length, that is 20 kilometer. 20 into 10 power 3, 20 kilometer. And the area is pi r square. Pi 3.14 r they are given. The radius 0.5 centimeter given. We have to convert into meters. So after that we are finding the resistance of the wire is this. Okay, the power, we have to compute the power loss. Okay, P equal to VI, I equal to P by V from this. Okay, this is 1 megawatt power, that is 10 power 6 watts, voltage to 220, then this is the current. So the power loss during the transmission is I square R. I square, this is square into R. So this is the power loss, 0.81 10 power 8. But actually we have to transfer only 1 megawatt, that is 10 power 6. So here power loss itself is 10 power 8 is coming. Okay, that is not at all feasible. Okay, not feasible. It is more than the transmitted power. Okay, so now the second case, we are stepping up the transformer. Okay, we are stepping up the voltage to 11,000 volts and transmitting. So what will be the current? So this is the current. Okay, now we compute the power again, current into resistance. So now we are the power loss is 3.3 10 power 4 only. We are transmitting 10 power 6, that is 1 megawatt. Power loss is less than the our transmitted power. So this is feasible. This is only 3.3% of the one. This loss is only 3.3% of the load power, that is 1 megawatt. So now this, when you step up the voltage and transmit, then that is feasible. Okay, this is feasibility when you transfer the power the high voltage. Consider the LCR circuit shown. Find the current. Okay. Okay, you can go through this because R parallel the voltage source. This R is parallel, the same voltage appear across the resistor and across these two combinations. A resistor and these two capacitor and inductor. Okay, you can go through it. For an LCR circuit driven frequency, this is the angular frequency at resonance. The equation reads, okay, identify. So okay, you can go through the answers for this. Okay.